Right. So this is the last slide you all saw last week. It's how to calculate the amount of heat energy required to do something. Remember, heat is a type of energy. So if you want to raise the temperature of something or change the state of something, like from solid to liquid, it requires heat energy. And the symbol for that we're going to be using is HE. And all energy, no matter what kind of energy, is measured in joules. And the symbol for that is, as you all may have remembered, is capital J. So there's one formula to calculate. Let's quickly go through this. We use the term specific heat capacity when there is no change in state, but a change in temperature. For example, sometimes you apply heat to something. Let's say it's a solid. If it's a solid at the beginning of the question and at the end of the question, it's still a solid, then that's a specific heat capacity question, meaning that there's no change in state. So if you have a liquid at the beginning of a question and at the end of the question, it's still a liquid, then we will be using this formula. Now, this formula is pretty easy to use. It's pretty easy to understand, actually. The M will be stands for the mass. So it's the mass of the solid or the mass of the liquid or the mass of the gas. Now, I would prefer if it's in kilograms. So you got to be very careful, right? The specific heat capacity, let me write this a little bit better, a little more spaced out for you guys. In this formula, the mass will be usually measured in kilograms. The specific heat capacity is usually, a keyword, usually, measured in joules per kilogram degrees Celsius or Kelvin. It can be degrees Celsius or Kelvin, because there are two ways to measure what? Temperature. And the temperature will most likely be in degrees Celsius. Now, one thing to note, right? Let's put back the joules here. Heat energy is measured in joules. However, you have to be real careful. Sometimes the specific heat capacity is not given in joules per kilogram degrees Celsius. Instead, it's measured in joules per gram, not kilograms, degrees Celsius. Now, when this happens, whenever they give you the specific heat capacity and it have grams, you have to make sure your mass is also in grams, not kilograms, right? So that's a small thing to look out for. And by the way, delta T stands for the change in temperature, but TEMP here. Now, change in temperature is different to temperature. For example, if I have a piece of metal and the piece of metal is 20 degrees Celsius, and then the temperature is increased to 25 degrees Celsius, the change in temperature is 5 because it went from 20 to 25. So the change is 5. A lot of people mix up change in temperature with regular boring temperature. Right. Everyone take down the first formula with all my scribbles on it. Okay. So we're going to be looking out for all these little things. When the examiner will try to trick you, like instead of using kilograms, he will use grams. And the only one thing is going to make us accustomed with these formulas: practice. Right? So only take down everything associated with the first formula, and then I will explain the second formula, and then we will move on. So the second formula has to do with something called latent heat. So latent heat is a special type of heat where it does not create a change in temperature. And I think I had mentioned this last week. Well, what latent heat does, instead of raising or changing the temperature of something, it changes the state. Like in this one, the solid will change to what? A liquid, or the liquid may start off as a liquid and then end up as a gas. There will be a change in state, but no change in temperature. To calculate the energy associated with that, right? Remember, heat energy is always measured in joules, right? M stands for what? Mass, as usual, right? And usually the mass is in kilograms, and the latent heat is measured in joules per kilogram. But just like the specific heat capacity, right? Right? But just like specific heat capacity, if the latent heat is given in grams, not kilograms, you have to make sure the mass matches up, right? So once again, latent heat is used for a change in state, and this formula is also used when there is no change in temperature, right? And latent heat is found very commonly among us. For example, when a block of ice melts, ice, you usually associate ice with 0 degrees Celsius. Water freezes at 0 degrees Celsius. But when ice now melts and it forms water, like I'm talking about it now melt, the water is at 0 degrees Celsius. So this is a case of what? Latent heat. It's changing from a solid to a liquid, from solid ice to obviously liquid water. And there's no change in temperature, only a change in state. So the heat that was applied to the ice was not invested in changing the temperature. Instead, it was invested in changing the state. Take down the second formula. Let me know when you guys are ready. Right, so you're gonna get a lot of practice today, guys. Don't let the formulas scare you, right? I have so much different questions with so many different tricks in it. All right, so at the top of the screen, right, just to make things easy for the time being, right, you have all the formulas and all the information. This is like a training wheels, right? In the physics exam, there is no formula sheet, right? You have to memorize everything. And it has certain things you don't need to memorize. Certain things like the specific heat capacity of certain items or materials will be given to you at the bottom of the question or at the top of the question. Also, when it comes to latent heat, there are two different types of latent heat. There's one called fusion, and that means it's changing from a solid to a liquid or a liquid back to a solid. But there's no change in temperature because latent heat has nothing to do with a change in temperature. And another type of latent heat is vaporization. Vaporization is when it's changing from a liquid to a gas or a gas back to a liquid. Anytime something is dealing with vaporization, they will use the letter V somehow. The V will stand for vaporization, and you're going to be seeing it. And of course, if it's fusion, it's going to be what? The letter F, right? I know the writing is kind of small, but when I reach it, the small letters, I will talk about it or write it bigger for you guys and whatnot. All right. So the first things first. Let's say we're stranded on a deserted island, and we make a spear out of metal. So we're back in the caveman days here, right? Here's what we're gonna do. We're gonna put the spear over a fire. The initial temperature of the spear was 28 degrees. So that's before we started to heat it up. And then after heating it up, it went up to how much? 120 degrees, which makes sense, right? When you put something on a flame, it's supposed to get warmer most of the times. We're going to assume that the piece of metal did not melt. It did not melt. And the mass is 92 grams. What kind of question is this? Is it a specific heat capacity question or a latent heat question? Right? That's the first thing we have to decide, so we know which formula to focus on. Right? So let me see you guys. Right? And a lot of people are getting it correct. It's a specific heat capacity question. So we have to focus on this formula, right? So the first thing, once we identify the formula, well, we should probably write the formula, okay? Because there's no change in state. At the beginning of the question, it was a solid piece of metal, and we assuming it not melting. So at the end of the question, it's still a solid. So let's write down the formula. You actually get marks in the exam for writing down the formula. Simple stuff. Right. Great. So if you look at the top of the question, they gave you they have this SHH. So we paying attention to the specific heat capacity. Now you see the letter I. Now, I know you can't see it there, but at the top of the question, they wrote SHC. That stands for specific heat capacity, and they have the letter I. The letter I stands for the substance. The I stands for iron. Don't worry, the examiner will make it perfectly clear. So let's put in the values here. To calculate the amount of heat energy required, right? The specific heat capacity of the material in question is 320. So we put 320 here, right? Anybody wants to tell me what's the change in temperature? What's the change in temperature? It started off at 28 and then it went to 120. What would be the change in temperature? It's a simple subtraction question, right? You're taking 120 and you minus the 28. That gives you the change. So 120 minus 28 is 92 degrees. What do I put for the mass? What am I going to put for the mass? I'm trying to trick you here. So see if you can figure out the trick here. Right, so the trick is, remember, our specific heat capacity, if you look at it, it's in kilograms. Now, it just so happened the mass is also 92. That's pure coincidence. I didn't expect that. The mass is in grams. It's 92 grams. It needs to be in what? Kilograms. Right? So you all need to convert that to kilograms. Right? So you have to divide it by what? 1,000. Right. So you guys are telling me the correct thing. So take the 92 and divide it by 1,000. Just like in primary school, that's how you convert what? Grams to kilograms. So it's 92 divided by 1,000, which is 0.092 kilograms. And this is what you put for the mass, 0.092, because that matches up with the units of the specific heat capacity. So all you have to do is multiply everything here, and you're finished, mostly finished. So let's multiply that out now. 0.092 multiplied by 320 multiply by 92. And I'm getting this. 2708.48. And a lot of people are asking me, or either getting the units wrong. Remember, we're calculating heat energy. All energy, once we use the correct units in the formula, and we did use the correct units in the formula, all energy is measured in joules, just plain old boring joules. So just put a capital J. It has no joules per gram or nothing. We use all the correct units in the formula. So that means our heat energy, like all other energy, will just come out in plain old boring joules. So you just put in a capital J and you're good to go. How would you rate this question? Right? I think I mentioned this last week. Whenever you are using a formula, right? Let me just show you. In physics, it is given real extra marks for stating formulas, but not just stating a formula. This is what you just have to do in a physics exam to get full marks, right? I just clean up some space here, right? Usually before you start to use a formula, you can write down the formula, but then you need to state what each letter represents. You only have to do it for once in the exam. Once you do it once, you don't have to do it complete like this again. Like you say the HE, this stands for what? Heat, energy, and in brackets, put the units that you're using. This is mass, and in brackets, put kilograms. And then you have to spell out, this is what? Specific heat capacity. Well, you need to spell it out in the exam, and in brackets, you need to put what? The units. And this stands for what? Change in temperature. So you can put little arrows like this to what each symbol means or each letter means, state the units, and then you start the question. Every single formula in the physics exam, you have to do that. Otherwise, you do not get full marks. Right? Now, I know today's class, so I don't expect you to do that in today's class, right? You are just focusing on getting the questions correct today and writing, the formulas. But for term tests and for exam, make sure you do it like that for every single formula, right? So just some advice there. Let's move on. Oh, we have a little puzzle here. So I came up with this one this morning, right? It's a riddle, right? Without Googling this, right? I know you all can Google any riddle. Let's see if we can get out this question. What great invention lets you see through a wall? It's a 1, 2, 3, 4, 5, 6 letter word, right? And it has an O in it. I found this one was pretty interesting, right? I had asked someone this and they couldn't get it. It's a window. It's kind of silly, but it's a window, right? A window allows you to see through a wall. It can't be a mirror. All right, guys. All right, let's move on. So here we have a slightly different question, right? We have an axe this time. So we're going to heat up, right? An axe. Read the question, right? It has some, the axe is made up of brass, right? So all the information is given over here in this little square bubble here. And of course, I have the formulas in the white rectangle above. Just give it a try. Just give it a try. It doesn't matter if you get it wrong. But there's a ton of tricks in this question. Good luck, right? Well, I think we established that we're using the first formula, right? The normal formula we used just now, right? Because it's what? No change in temperature. So let's start off here. Sorry, make a mistake there. Heat energy is equal to mass multiplied by specific heat capacity multiplied by the change in temperature. Now, keep in mind, this stands for change in temperature. That's a key phrase there. Change in temperature is not the same thing as just plain old temperature. Change in temperature tells you how much it increased by, or in some cases, decreased by. Did they give you the heat energy? Yes, they gave you the heat energy outright. But I tried to trick you. They didn't give you it in joules. What does a K stand for? Kilo. When you see a capital K, that means kilo. Kilo means you have to multiply it by 1,000, just like how kilograms means 8,000 grams. Kilojoules means 8,000 joules. So you have to take the 58 and multiply it by 1,000. How much people genuinely forgot to do that? Well, not forgot, but probably you didn't realize that the heat energy, you had to multiply it by 1,000 plus. Be honest, it doesn't matter if you get it wrong. Like I said, this is just practice, right? We are allowed to get things wrong, but you have to try, right? The mass, was the mass given in the correct units? Yes or no? Was the mass, right? The mass was given in correct units because the specific heat capacity had a kilograms in it, and the mass is also kilograms, right? So no tricks there. 0.45 kilograms goes there. They gave you the specific heat capacity of the brass is 380. And of course, we don't know the actual change in temperature. So this is where your maths comes in, your algebra skills. We're going to try to solve for the change in temperature. So let's begin here. You have 58,000. Let's take 0.45 and multiply it by how much? 0.45 by 380. 171, right? I'm getting, and then you multiply by the change in temperature. Like when you combine these two, you get the 171. So take the multiply, throw it across, you get your divide. So let's divide it, and that will give us our change in temperature. 58,000 divided by 171. Did anybody get this? Let me use a different color here. 339.18 degrees Celsius. That looking correct there, right? I double check it on my calculator. It seems correct. But is that the final answer you want to give to the examiner? Think about it. Is that the final answer? Right, some people figured it out. Remember, this is the change in temperature. This is how much it changed by. The initial temperature was 29 degrees Celsius. So when it started the experiment, it was firstly at 29 degrees Celsius. Now it changed by 339. So the final temperature, we have to add it to the 29 degrees to get the change. You start off at 29 and then you change by that amount. So you take the 339.18 and you add the 29 and you'll get your final answer. I'll write it right here in red. 368.18 degrees Celsius. This is your final answer. Putting some arrows by it here. Right? So a question like this is worth probably a good 5 marks in the exam. Right? So take down everything. Take down everything. All right, so here we have another one here. Let's describe what's going on here. So this question is a little bit different. How much energy is needed to just melt 0.4 kilograms of iron starting from 28 degrees Celsius? We're going to assume that the melting point of iron is 850 degrees Celsius. Now, this one here is different because there's going to be a change in state because we're melting something. So it's going to start off as a metal and then change into a liquid. This question is a mixture of both formulas. Just asking you, right? We know latent heat is involved somehow. Is it going to be latent heat of fusion or latent heat of vaporization? Which one is it going to be? Right, it's going to be fusion because we're melting a piece of metal. So it's going from solid to a liquid. So this one is fusion. So the values for iron are given up here. So we have to use the IFI. The I, let me write it back here properly for you. Not I, LFI was given as what? 125 joules per kilograms. The F stands for fusion and the letter I stands for iron. So you know the material. So this is the latent heat of fusion for iron. So at some point we're using the 125. But it's not as straightforward as you think. Let's do a flow chart here. Initially, we have a solid piece of iron. I think we know this. The initial temperature of the iron is 28 degrees Celsius. Before you could melt the iron, we have to raise its temperature to reach the melting point. So we're going to heat this piece of iron, which is a solid, and then heat it until it's still a solid, so it remains a solid, but it has to reach 850 degrees Celsius, but it's still a solid. Now, when the solid metal reaches 850, then it can start to melt. Now, when something melts or changes state, the temperature remains the same. We mentioned this last week, right? So when the iron now melts, it will change to liquid iron, but that new liquid, that now form, it's also at 850 degrees Celsius. Everybody with me so far? You have to heat up the iron to 850, but it remains a solid. And when it reaches 850, then it can begin to melt because that's the melting point of iron. I want you all to draw this flow chart for me, but don't draw it small. We're going to have to put work in between. We're going to have to put some work in here, and we're going to have to put some work in here. All right, so take a 20 seconds for that, and I'll show you the working for it. Marks in it. All right, so we have two sets of working to do. One, between going from a solid and remaining as a solid. Which one are we going to use? The red formula or the blue formula? Which one would we use for the first set of working? Red formula or the blue formula? The one with specific heat capacity or the one with latent heat? What do you all think? Yeah, let's call it color if you want. Might be easier. It's definitely the red. So let's put down the formula here, right? So HE is equal to M by specific heat capacity by changing temperature. Now can I squeeze it in there? All right, so let's do the working for this piece. How much heat energy is required for this portion? Well, do we have the mass of the metal? Yes, we have the mass of the metal. The total is 0.4 kilograms, so 0.4. The specific heat capacity of iron, I have it here. Specific heat capacity of iron is 320. And the change in temperature is easy. I think everybody knows how to do that now. It went from 28 to 850, so you have to minus them. 850 minus 28 is 822. Work out this piece for me. And that only gives you the heat energy for that portion, not for the entire question as yet. Right? And notice they gave us the mass in kilograms, so I didn't have to change anything. Right, so let me, not like I don't trust you all, but I have to work it out myself. 20 answers are coming up. Caramello, check it back now. I get a flat answer. I'm getting, this is what I am seeing. I am seeing 105,216 joules. I didn't get any decimals at all, right? So check, for those who got decimals, check it back. It's just a matter of multiplying these three numbers, nothing else, nothing else. All right. Once we reach there and we know how much energy is used for that portion, well, then we have to calculate the energy for the second portion. It has to go from a solid to a liquid. Now, when things change state, I know I'm saying it over and over, but I need it to stick. When things now change state, the temperature is always remain the same, always. So if it's going from a solid to a liquid, that is a change in state. So we know we're using the blue formula. So He, mass by the latent heat of fusion of iron, right? So let's calculate the heat energy for this portion. The mass of the iron is still 0.4, right? Melting it is not going to change the mass. And what's the specific latent heat of fusion of iron? Well, I gave it to you. The examiner will give it to you in the exam, right? F stands for fusion, and the letter I will obviously stand for iron, the name of the material. And that's just a real small value, 125 or whatever. I don't think that's a realistic value, but let's just go with that. That's what the examiner gave us. Got a real small answer here. So this is going to be 0.4 by 125. Hey, easy. What do you think we have to do now to get the total amount of energy? And common sense will say add both answers because you want the total amount of energy for the entire process. So you find each portion and then you add it up, right? So let me add it up here. I don't know why I need a calculator for this, but I can't do it in my head right now. So the total amount of heat energy is 105,266, which I was unable to do in my head. That's your final answer. Of course, you're going to get about 6 or 7 marks, but you're only going to get that 6 or 7 marks if you write the formula and state what each symbol means and the units required for each symbol. Right? I've seen a lot of students just write down the formula halfway like this without explaining it. They get the correct answer and everything, and they still get a 2 in physics. There's a reason for it. You got to be very, very complete. Pretend you're writing a textbook. Pretend you're writing something that you would want to read and be able to understand. Pretend you're selling that document to someone. Because if someone did a halfway document and didn't explain what each part of the explanation means, you will get angry, right? You'll be like, but this is a waste of time. So I always tell people, pretend, hey, you're selling that document to somebody else and you want it to be clear and good. Right. I don't know if you all saw this one already, right? For those who came to class for integrated science or HSB, I don't know if you all are in those classes. You think you could guess the picture behind? What is the paper hiding? Somebody got it out. Chanel got it out. Rostand got it out. I try to make these things hard, but these picture things are always easy for some reason. Well, two people got it wrong. It's definitely not a puppy, and it's definitely not a cat. And it's not a duck. I'm gonna burn some more holes into this, right? The wizard will burn some holes here. It's not a rabbit, but good guess though. If I didn't know the answer, I probably would have said a rabbit. Reza, correct. Yeah, most people getting it correct now. Right. Right. So for those who guessed something starting with the letter S, you are correct. Yeah. It's a seal. All right. Great. So for those who got it out, you have some good eyesight. You have some good eyesight. Or you probably have a pet seal home, and this picture is no stranger to you all. Let's move on. All right. There's one thing here. I think I skipped. I'll make sure I'm skip it. Right. So here, something is missing here. All right. So here we have one of these super questions, right? It's one of those terrible questions, but it's worth a ton of marks in the exam. A question long like this will have a part A, a part B, a part C, and a part D in the exam. So the examiner will break up this question into different pieces. And by the time you add up all the marks for this question, you're walking away with 8 or 9 marks in the exam. First things first, right? Let me just explain what's going on here. You are going to take a block of ice and melt it. First things first, is ice always at 0 degrees? Yes or no? Is ice always at 0 degrees? Right, the answer to that is no, right? It's just a common misconception. And it's a trigger word now. When you hear ice, you just remember, hey, water freezes at 0 degrees. So you think ice is always at 0 degrees. This is just simply not true. Ice could be minus 20 degrees. It could be minus 40 degrees, right? Ice could get really cold, right? So let me explain what you're going to do. Apparently, let's pretend you're trapped somewhere in Alaska and you want some water to drink. So you take a block of very cold ice and you're going to melt it. Not only melt it, you're going to boil it, and for some reason, change it to steam. I'm not too sure why you're changing it to steam if you're thirsty, but let me just assume. You'll realize this is not a question simply about heating ice. It has a lot of state changes because ice is solid and your end product, which is steam, is a gas. So, and in between, it has to change to water. So it have plenty change of states here. Solid to liquid and liquid to gas. Let's go through this step by step. Watch me work it out first, and it's going to be a lot of work in it. But after I work it out, then you could take down everything. So you know how to space it out so it fits on your piece of paper. So apparently, the ice starts off at minus 5 degrees Celsius. Anything with W is water. So anything with a W is water. Water. And of course, for ice, I write the word ice. You notice all your values have kilograms in it. So at the beginning of the question, I tried to trick you. The examiner tried to mislead you. You want to vaporize 250 grams of ice. The first trick here is convert that grams to kilograms. Quickly do that step for me at least, because a lot of people would have worked with the grams throughout the question, and then everything going to be wrong. So we all know how to convert grams to kilograms. We just simply divide by 1,000. Right, so that I can do in my head. All right. So here's what. Before we can melt the ice, remember the ice starts off at -5 degrees. Solid ice will begin to melt at 0 degrees. So we have to change the solid ice at -5 degrees, and it remains solid ice at 0 degrees. Which formula do we use? I'm going to color code this, right? Do we use the red formula or the blue formula for the first part of the working? Red or blue? It definitely has to be red. So I'm going to write back here. H is going to be mass by specific heat capacity by the change in, forgive me for leaving out the small e here. It's kind of hard to write when you're writing this small. All right, so let's see what values we have to put in here. The mass is 0.25. That's the mass of the ice. What are we going to put for SHC? Let me see if you all can get that. Look at the top of the page and tell me what value we are going to put for SHC. I want to see if you all fall for this. Which value are we going to put over there? Right, Alia, correct. Right, Salamatu, correct. Ishan, correct. The Spring, correct. Right, Princess, correct. Great. Right, remember, we're dealing with ice here. And the specific heat capacity of ice, it will be given to you by the examiner. You don't have to worry, right? So it's 2100. How much is the change in temperature? Somebody said green or purple, right? It wasn't an or question, right? Remember, the green one is the fusion of water. That's a completely different thing, right? So the change in temperature is always a positive value. Remember that, right? The change in temperature is always a positive value. So it went from -5 to 0. So I know it's tempting to put -5, but change in temperature is always positive for this topic. So we put in 5 because it went from -5 and then it heated up to 0. Calculate this portion for me. That tells you how much energy was used for that portion. All right, let me work it out here. And I'm getting 2,625 joules. Make sure you see it on your calculator and don't assume you could do it, right? Make sure you could do it. All right, so we have the first part of everything done. The ice has cooled down to 0 degrees, well, warmed up, I mean cooled down, and warmed up to 0 degrees. So the ice is ready to melt now. Now, when ice now melts, it will change to water. But that new water will also be at 0. When something now melts, the temperature does not change. Which color formula are we going to use from on top here now? Red or blue? I think it's the blue. So let's write because it's a fusion. This here is a latent heat question. No change in temperature, only a change in state. So let's write the formula. He is equal to mass by. The mass of the ice has not changed. But what are we going to put here? Look at all the values on top. Call the color. It's either red, blue, green, or purple. Which one do you think goes there? It's a latent heat question. So, I mean, common sense would say it's between what? The blue and the green. Right? Because it's a latent heat value. The red is specific heat capacity and the purple is specific. We need something with an L. I think the answer would be green. And based on what most people are saying, you guys are getting it correct. Because this is LFW. What does the F stand for? Fusion. Fusion has to do with what? going from a solid to a liquid or a liquid to a solid. It deals with solids and liquids. Ice is solid, water is a liquid, right? So, and the W stands for water here. They could have put ice to it, but the fusion of water means it's what's changing into water. And it's in kilograms, so we put 334,000, right? So multiply that for me now. Let's see what we get here. This is what I am seeing. Right. Now that the ice has finally melted, we want to bring it to steam. But before you could steam water, and you have to bring it to a boiling first. Well, water won't change to steam unless it what? Boils. So we have to heat up this new water, which is at 0 degrees Celsius, and heat it up to liquid water at 100 degrees Celsius. Which formula are we going to use for this portion? Red or blue? You guys are getting it correct, right? The answers are popping up on the screen. It's the red formula because there is a change in temperature, but no change in state. So write back the formula here. H is equal to mass by specific heat capacity. Remember, we're dealing with water now. The mass of the water is still 0.25. What value are we going to use for the specific heat capacity here? What value? Right, Ishan, correct? Right, Tiffany, so fiery. Brianna, you sure? Remember, we're dealing with water, and it's a specific heat capacity. So shouldn't it be 4,200? This W stands for the specific heat capacity of water. The examiner will use little symbols. So W will naturally stand for water. All right. So it's 4,200. And how much is the change in temperature? What are we going to put for the change in temperature for that portion of the question? 100. Correct, guys. Because it went from 0 to 100. So multiply that out. That's how much energy. This is what I am seeing. Huh? If I get it wrong, let me know. I will make some mistakes there. I can see it already. All right. So we all agree it's the blue formula, actually, right? It's the blue formula because it's a change in what? State. It went from a liquid to a gas, where steam is gas, right? So HE is mass by the latent heat. Now, what kind of latent heat is this? Is it fusion or vaporization? Which one do you think it is? There are two types of latent. It's either it's fusion or vaporization, right? You guys are shouting out the correct thing. It's vaporization because it's going from a liquid to a gas. All right, so let's see what I did wrong. So you have 0.25 as the mass. And the latent heat of vaporization, that's the blue value here. Look at that, V and W. So the V naturally stands for vaporization and the W stands for water. Now, I don't know if you all know how to type in, well, different calculators have it different, but to type in standard form, this is 2.26 multiplied by 10 to the power 6, right? I'm not going to be able to help you type in this on your calculator because every model of calculator is different, but 10 to the power 6 is the same thing as a million. I could tell you that. So if you can't find multiply by 10 to the power 6, you're just multiplying 2.26 by 1,000,000, a 1 with 6 zeros. That should make it easier for you. So let me work this out now. Let's see what I get. 2.26 multiply by, oh, I did it wrong, guys. I'm getting this 565,000 joules. And most people were telling me that. So I don't know what I did wrong, right? But that's what happens when you don't put on work in and you just try to do everything like a hero on the calculator. Right, so for people who got this answer, congratulations. For those who didn't, well, at least you could see your mistake, right? Is the question done there? Well, what do you guys think? Is the question finished? No. We have one small thing to do again. Remember, they want the total energy. So what do we have to do? We have to add up all the answers, right? The total energy is the energy for this portion, plus the energy for this portion, plus for this portion, and this portion. So add up all, and then you're finished, right? Oh, these numbers, oops. These numbers are pretty large. 2, 6, 2, 5. If these numbers could be the amount of money I find underneath my bed later, I would be so happy. Five, 0, 0. I'm getting this. I hope I did it correct. My final answer, I got a nice color here. Nice little orange here. 7, 5, 6, 1, 2, 5 joules. All right. Oh, that is worth 8 or 9 marks. I think we had to work for that. So guys, as promised, I'm going to give you all a few minutes to take down everything there on the screen. Make sure now, you might have to turn your book sideways. So the whole diagram could fit now in your books. But 3 minutes, I think that should be more than enough. 3 minutes, and I know some of you all probably wrote some of it already. So let me know when you're finished. And of course, when you're ready to move on. All right, so let me see what's going on with this question. All right, so this here is another one, but you're gonna try this one on your own. Let's see what you come up with, right? So if you get out this question, just know you're getting about 8 or 9 marks in the exam for this particular question. So this is where you practice what we just learned. I think you'll need about 5 minutes. I don't think you could do a question like this in 2 minutes. So good luck, guys. And of course, make sure and send your answers across and communicate with me. So the first part, you start off with solid ice and you move to still solid ice. So in the first section, well, there's no change in state. So I know it's the red formula. So let me color code it, right? So for the first part, I'll use the red formula. Oops, I spelled specific heat capacity wrong for some reason. Shame. Specific heat capacity by the change in temperature. So, like I said, the specific heat capacity was of ice. Oh, right now we're dealing with ice. Where's the ice value? The specific heat capacity of ice is 2.1. It's the purple value. And it's in grams. And my mass is also in grams. So everything match up perfect. There's no need for conversions. The mass is 32. The specific heat capacity is 2.1. And the change in temperature is 12. Now remember, I said the change in temperature will always be a positive value. So it went from effectively from 12 to 0. Leave it as positive. Let's multiply that. 32 by 2.1 by 12. How much people can at least agree with the first part? I got 806.4 joules. Let me know if I made any mistakes there. Right? Right. So I think some people made some mistakes. Like you did some conversions by mistake, like you divided by 1,000. There was no need to divide anything by 1,000 because the mass was in grams and the specific heat capacity was also in grams, right? Shane, you saw your mistake, right? I think you divided everything by 1,000. There was no need to divide anything by 1,000. Everything was perfectly matched up, right? Great. For the second part of the question, it goes from solid ice to liquid water. And it was 0 and it remained 0. So there was no change in temperature. So this is definitely what? A blue formula. So heat energy is mass by the latent heat of fusion. This is a fusion because it's going from solid to a liquid. The mass is still 32 grams. And the latent heat of fusion of water, you notice they give you it in grams as well. So everything match up, No need to change anything. Just multiply those two things and you're on your way. I got this 10,688 joules. For the third part, it starts off as water and we just bring it to a boil. But it's still water, right? So there's no change in what? State. Great. So I think that's your red formula. So heat energy is mass by specific heat capacity by the change in temperature. So the mass is still 32. Specific heat capacity of water is 4.2, also given in grams. And the change in temperature is 100. So this one is easy, right? Multiply it out. And when you get all three answers, you simply add it up. This is what I am getting. So add up all your values now, and that will just simply give you the total energy involved in this process. When I add up all three, now running out of space to write my answer, I'll just write it in the middle here for the final answer, right? I am getting 24934.4 joules. I think I did it correct, but you could verify it. So I know some of you probably saw this if you came to integrated science class. I'm running in one material for a little while. Got to reuse stuff from different classes. So this castle is under attack, and only one person is going to survive. Choose your survivor. Who do you think is going to survive? Let me know on the chat, right? One by one, they will perish in this battle. I already know the answer for this one, so I can't play with you all. Let me know in the chat now, guys. Who do you think will survive? Is it going to be Sir Adam, Maid Mary, King Abe, Sir Tom, Queen Ava, Prince Hoppy, Sir Paul, or Sir Harry to your extreme right? All right. All right, let's see. So you all have your bets in there, right? So the first person to perish is going to be, oh, Queen Ava. She's gone. She has an arrow in her there. Poor Queen Ava, gone. Next person to go is Sir Paul. Also got an arrow. Go on. So that's the archers. As soon as the archers leave, the catapults come in. And let's see who's next to go. Sir Adam is gone. Poor Sir Adam got crushed by a rock. Next person to go is Sir Tom. A lot of people chose Sir Tom, but he is gone. Next person to go. Oh, there's a dragon coming in, I believe. King Abe goes up into flame. Poor King Abe, not his kingdom anymore. Next person to go is Prince Happy, another favorite. Sorry, guys, a lot of people said Prince Happy. And there are two more people left. Choose, guys. I'll give you all a next shot. Who will survive between Maid Mary or Sir Harry? There are only two more people left. Let's see who's next to go. Next to go up in flames is poor Maid Mary. The winner is Sir Harry. And was anybody able to guess from the beginning? Was anybody lucky enough to guess Sir Harry? Oh, somebody actually won. All right, guys, let's go. All right, so here we have a scenario, a kind of, well, very realistic scenario. We all know the sun heats up things. Now, for example, just before the sun rises, if you were to go into a river, the water will be cold. But as the sun begins to rise throughout the day, obviously the sun will begin to heat up the water in the river or stream, and the water gradually becomes warmer. This has to do something with heat. So let's see what this question is about. We're going to be calculating something called power, right? Now, before you even move on, right? Power is different from energy. So I thought this was probably a good time to bring up power. To calculate power, the symbol P is work or energy, right? Work over time. Now, here's the thing. Work and energy are effectively the same thing. And of course, energy could be what? Heat energy. So some textbooks, instead of having a W here, will have the letter E. So to calculate power, you just have to take the work and divide it by time. That is a general formula right throughout physics. However, your time has to be in seconds, not hours, not minutes, for this formula to work. And power is measured in something called watts, whose symbol is capital W. So to do this question, it's a normal heat question. But afterwards, once you calculate the heat or energy, to complete the question, you just divide it by the time it took for the entire question to unfold. And when you divide those two things, you will get your power. Good luck. See if you could calculate this one for me. Right? It's way easier than you think. Don't overthink it. Believe me. And this question, it's not worth as much as the previous questions, but you can still walk away with 6 marks easy. All we're doing is just raising the temperature of the water. So to calculate the heat energy required is the mass of the water by the specific heat capacity of the water by what? The change in temperature. The mass is how much? It was 2,000 kilograms. And the specific heat capacity of water is given in kilograms. So no tricks there. The change in temperature, it went from 16 to 35. 35 minus 16. 19, I think that's correct so far. Right? Nothing amazing there, right? 2,000 by 4,200 by 19. And I'm getting a huge number. 1596 with 5 zeros. 1, 2, 3, 4, 5 joules. So here's what we have: the energy. This here is the energy or work. But we want to calculate power. We're almost there. We just need the time now. But time has to be in seconds. For spite, I gave you 10 hours and minutes. So you have to convert 2 hours and 45 minutes to seconds. Now, in every hour, in case you didn't know, there's 3,600 seconds. In case you decide to sit down one day and out of boredom, count for 1 hour, you'll get 3,600. So, and we all know in a minute, there are 60 seconds. So all we have to do now is multiply. I think this is basic maths here, right? 2 by 3,600, that's 7,200 seconds. And 45 by 60, that's 2,700 seconds. Add up these two, and you'll get the total amount of seconds, right? Anybody can agree with this? That's how much seconds it took. 2 hours and 45 minutes is really 9,900 seconds, okay? So the underneath value, we have it now. So we are taking this huge number and dividing it by 9900, and that will give us the power. Because power is work divided by time. Work and energy is the same thing. So let's divide that. 1596. 1, 2, 3, 4, 5 divided by 9900. I got this as a cool looking number, I must say. I get my orange here. I am getting this amount of watts. 16,121.12 watts. Anybody else can agree with that? That's my power. Make sure you see it on your calculator. Once you get it, guys, right? This now.